Hi, I'm Steve Baird. I work at Adacore, and I'm also a member of the language maintenance committees for both Ada and Spark. And I'm going to be talking about levels of software assurance in Spark. The main point here is that formal verification is not a all or nothing proposition. There's an interesting conversation you can have about problems with mixing proven and unproven code. That's not what we're talking about today, although it's an interesting topic. What's going on today is it's really an artifact of the Spark tool architecture, where there's one pass that does what's called flow analysis, and it determines whether for example, here we have a subprogram, and apparently there's some global variable, some global state somewhere named XL and gyro that are queried that are read in the body of this procedure stabilized, and there's also something named rotors that is both read and modified. And this just verifies that in fact the implementation does what the specification says that it does. And there's no proofs involved here, where there's no, the stuff you sort of think of when you think about Spark is not in this phase, and yet that's the second phase, where you get what in Ada are runtime checks. Ada defines this pre-business, which says that when you call this subprogram, there's a runtime check that the incoming value of the mode parameter is equal to off, which presumably is an enumeration type, and that when the procedure returns, the post condition gets checked. And this is saying that if the outgoing value of the success parameter is true, then some function named delta change ought to return true when invoked with the incoming old value of rotors and the outgoing new value of rotors. So anyway, there's these two different chunks of the implementation, and they sort of naturally lead to these different levels, which each build on each other. The first one we call Stone, and this is just saying Spark is a subset of Ada, and this just says stick with the subset. No further checks. Just don't implement don't use any of the constructs that are in Ada but not in Spark. This includes, well, currently I'll talk a little bit more about it later, but one of the big restrictions right now today is no pointers. There's restrictions on concurrency. You have to stick with something called the Ravenscar profile, so that some of the no rendezvous. Anyway, expressions don't get to have side effects. That's another big one. But anyway, the tools enforce this, and so that's the first level. And then the second level is essentially saying that you make it through the flow analysis phase. And this is there's a lot of value here. Just we haven't done any proofs at all. But this catches uninitialized data. It ensures it detects race conditions, so there's a lot of it does a lot of useful stuff. And indeed, if you have users written specifications for what gets read and what gets written by a given subprogram, it will verify that they are indeed correct, that the implementation does what the specification says it's supposed to do. But so that's bronze level, is saying that you make it through all the data flow checks. Silver level is what I sort of think of as when people think of just Spark. I think they're thinking about this. And what this is saying is Ada defines lots of runtime checks. For example, indexing into an array, there's a check that the bounds are in value, or numeric overflow. Various range checks, division by 0. And in Spark, instead of a runtime check, well, I shouldn't say instead, because the dynamic semantics of Spark are simply those of Ada. Spark doesn't have any unique dynamics. The runtime behavior of a Spark program is the runtime of the same program, the behavior of the same program as viewed as an Ada program. But anyhow, every runtime check introduces a proof obligation. And under the covers, users don't have to be aware of this, but there's SMT solvers being invoked and until you've proven that this check is going to succeed at runtime, you're not done with compilation, and I use the word in a very broad sense, if you're trying to get things to the silver level. At the silver level, you're not done until you've proven statically that all these runtime checks are going to succeed. And that's a very useful property, but you still need testing and so on, because knowing that your program runs and doesn't fail any runtime checks is not at all the same thing as knowing that it does what you had in mind. I mean, suppose I had a piece of software that's supposed to be the flight controller for an airplane, and it's the null procedure. It does absolutely nothing. Well, we could get that to the silver level because it doesn't fail any runtime checks. So the gold level is where you start adding additional assertions to your code above and beyond what's necessary to get to the silver level. And this is just where you start saying, oh, there's other interesting properties of my program that I'd like to express. And it is a very rich, very expressive language with respect to assertions. You got pre and post conditions for subprograms. There's something called type invariants. There's something called subtype predicates. There's all sorts of constructs that are useful for just very concisely and very expressively expressing assertions about your program. And the thing is that assertion is just another runtime check, nothing particularly special about it. And so, like any other runtime check, it introduces a proof obligation. So if you can figure out a way to express whatever property you're interested in as an assertion, then now you can bring this powerful static proof machinery to bear on it and prove whatever it is that you're interested in about your program. There's also this business about the Liskov substitution principle that's for overriding operations, so that the precondition of the overrider implies that of the overridden, and the postcondition of the overridden implies that of the overrider, and that gets checked. Anyhow. And then last is the platinum level, which is full functional correctness. This is saying that this is sort of almost unattainable, but we can dream. This is where, it is attainable in smaller cases. This is where the fact that it passes all these proof obligations, that all these runtime checks are guaranteed to succeed, is enough to constrain it so that it couldn't possibly do anything other than what you wanted it to do. That you completely specified full functional correctness of the program. For example, usually this would be at a higher level, but let's say you're talking about a sort routine. At the gold level, you might specify that the output of your array is sorted. Say it takes an array of integers, and you might specify that it's sorted. But the implementation could then simply assign all zeros, and indeed that is sorted. So you probably also wanted to mention that it's a permutation, that the output is a permutation of the original incoming input, and that would maybe get you to the platinum level in this case. This is not some toy academic example. This is widely used in practice and becoming more so. I'm not going to go into detail here, but the point here is just that this 5-level scheme turns out to map nicely onto some existing software integrity levels or design assurance levels in other certification contexts. And these are some projects where Spark is being used in practice and has been. These were all done by Altran, who has partnered with Adacore, and this first one is a helicopter that's on a frigate, and Sholas is a program that monitors wind vectors and helps with takeoffs and landings and crew transfers. And the point is, it's interesting because it was the first SIL4 project the first software project to get SIL 4 certification in the UK. That's a C130OJ. You can tell it's the J because it's got the 6 rotors. The earlier version had 4. And the part of the project there that was written in Spark was the mission computer, which is responsible for most of the aircraft functions, although not engine control. And then the last one is IFACS, which is a air traffic control system developed for the National Air Traffic Services in the UK. This one's interesting. It generates 153,000 proofs, and they're all proven again from scratch every night. And it takes about 2 hours on a system that costs about $1,000. And so that's just a commit activity. You know, you make a change, and anytime you make a change, you just and it typically just takes a few seconds if you change the body of some module. If you change something that an interface that affects a lot of code, it might take 15 minutes. But that's just part of the normal maintenance activity. This diagram here is something that you would see up in the air traffic control up in the tower, and it's the axes are time and distance, and that red dot is saying that in 11 minutes, 2 aircraft are going to be 4 miles apart, and that's too close because the legal limit is 5 miles, and so the idea is to give the controllers a heads up to of problems that are coming up that need to be dealt with before they get to be real problems. And Thales, this is another example. This is just some case studies where Thales it's a French aerospace company, and they wanted to investigate, the real practical details of what's involved in doing this, and because they're interested in it from a very nuts and bolts point of view, and they did some case studies, and together they came up with this booklet which I have many copies. It's available online. I have many copies of it out there. I'd be delighted to give them away. I don't want to bring them home. I also have books on Spark, and anyway. So come see me if you want more, but this is just, as I say, is full of very practical nuts and bolts advice about what's involved in making use of Spark. And Spark is improving over time. At the stone level, the subset is increasing with more things are being added to and in particular Ada pointers. It's not there yet, but we have work in progress. I don't know if for those of you who are familiar with the single ownership model in the programming language Rust, where the idea is you can have pointers, but only a given object can only be pointed at by one other object. So you can have a linked list, you can't have a doubly linked list. And so that with this single ownership model, it doesn't introduce the aliasing problems that complicate analysis the way unrestricted use of pointers does. This is just an example of how under the covers, one of the things we get tremendous benefit from is that SMT solvers have become smarter, and we can't take any credit for that. We just use them, but it's wonderful. So that the tools need a lot less human hand-holding to for the proofs to go through, and this is just saying how much harder this was in 2005. And here and another place where things have gotten better is there are more CVC provers now. And so for example, you generate a proof obligation, and we run it through CVC4, which is an SMT solver, and maybe it can't prove it. So then we'll try again with Z3 or with AltErgo, and these are not things that Adacore developed. These are CodePeer is a static analysis tool that Adacore does develop. In fact, I work on it, but and that's another alternative way to prove things. And this is just an example of some code that generated various proof obligations and showing how some of them were discharged by CVC4, and of the ones that CVC4 didn't take care of, Alt-Ergo dealt with some of them. So this is just showing that how, in practice, this strategy of using multiple provers, and it's just, the user doesn't have to be aware of all this. I mean, you just click the box on the cover. You just click the box saying, "Oh, use multiple provers," or the precise details of what's going on here are not anything that the user needs to be concerned with. The VSTTE there is the Verified Software Theories Tool Experiment. And we're using, we've developed this notion of autoactive verification. And what I mean by that is it's interactive, not in the sense of using a proof assistant like Isabelle or Coq, but rather, if the proofs don't go through, you add more assertions. You take you presumably have some logic in your head why you believe this program is going to work correctly, and you just need to communicate that information to the tool. And one of the things that's a fairly powerful mechanism for doing this is the notion of ghost code, which is code that's used only for static analysis. You can execute it if you want to, but typically in production code you would disable all the ghost code. So you can have ghost subprograms, ghost variables, ghost, and all this stuff is just there in your code. It's not, it's in the same file, but it's all marked as ghost. And so when you disable the ghost code, it goes away. And there are rules. It's checked that indeed none of the ghost code will have any effect on non-ghost state. So that removing all the ghost code isn't going to change. I mean, it might change the timing of your program, but as far as the portable language-defined state of the program, deleting ghost code is not going to change the behavior of your program. And so that's and here's just an example. The blue is these are source lines of code. The blue is sort of the real code. The orangish brown is contracts specifying the pre and post conditions for subprograms, that sort of thing. And then the gray was ghost code, which is code that's present there, but it's only used in analysis. As I say, you can execute it if you want to, and that's useful in some cases, but typically in the production code, you would disable the ghost code. So the thing we want to take away here is that it's, as I say, it's not all or nothing, that there's levels and that each have their own cost-benefit point. That each level requires the previous one, and that the lower levels don't require as much work. And there's a good match between these existing certification levels and this 5-level model. That we have very practical advice available in this booklet from Thales, and that catchy names are easy to remember. And I'll leave you with these resources. In particular, libre.adacore.com is where all the free stuff is. If you want to download Spark and use it, it's there. It's available for free. The book that as I say, if you're interested in the booklet about the joint thing with Thales, that's available online here, or I've got a ton of copies out there in the lobby. And so, any questions?
Thanks to you. Thank you very much for supporting us as well as supporting Ada.
Sure.
Thank you.
Thank you.